See, all right, got a full screen now. And we're gonna do, let's see, uh, 6 to 8 problems maybe of the newer material. Written some things down so that I can do them all right here. Get my eraser. And we'll start with some integration problems. Let's take y equals x squared. And let's rotate it around the x-axis from -5 to 5. Again, you're pausing the video, and I'm just doing the problem. All right, so y equals x squared from -5 to 5. Bumpity, bumpity, rotating it around. So this is going to come out from the wall, and we're going to get something that looks like this, right? That area, that area, that area, that area, rotating around. Kind of looks like a cross section, looks like a butterfly, but you're rotating it around and you're getting, I don't know, interesting, especially right there at 0. I don't know if it breaks apart or not. Don't ask me. I don't know, but I'm going to write the calculation. All right. So this is a disk. This is just a disk. That's all it is. And a disk is pi integral from a to b, big R squared. And we're going to do it in terms of x, right? Because each of these radiuses, radii, I guess, that's your big R, right, is defined by x squared. And that y value depends upon the x. You know, if you put in a 3, then that's 9. All right, so pretty simple, -5 to 5. We've got big R is x squared, and we're squaring it, dx. We're done. Okay, but I don't want my model, my creation here to fall apart, because I really don't know what goes on right there. If you got one radius, scary. So I think we better rotate this around y equals 30. Now, I think I want to rotate this around y equals 30. Oh, yeah, because it just is bothering me, scaring me to death. I wonder if that's going to take care of the problem. I don't know. Let's find out. So now we got a washer method. So now we got something called the washer method. And we've got this shape here. And it looks like we still have the x-axis here. We're going to take that. And we're going to rotate it around. And so we're going to have something up here, right? Outside of the screen view. And so we got to define our big R and our little r. I think big R is not part of the -5 to 5 picture. But I think we can see big R is actually that, the outer edge. The outer edge is the bottom part of the shape. Right? That's our big R. Oh. And I think our mantra is top minus bottom. Big R is 30 minus 0. And I'm telling you, if you memorize top minus bottom, when you start working with negative axes, very helpful. So if you can do that from the get-go, that would be nice. Little r, right there. Little r is right there. And I guess that's x squared. And it looks like top minus bottom for little r is 30 minus x squared. Well, I guess we're cooking with gas now, a to b. Big R squared minus little r squared. And this is still in terms of dx. Okay, so I think we're ready to say pi from -5 to 5. Big R, let's just say 30. Big R squared, 900 if you want to say that, minus little r, good thing for parentheses here, little r, 30 minus x squared. We've got to remember to square it. And it's in terms of dx. There we go. Let's put that in brackets, because this nominal term is distributed. The numerics of that is necessary. And I'm hoping that that problem's starting to follow it a little better. And if you're following it a little better, maybe you've already followed it to begin with. Maybe you're doing it a little quicker. Maybe you're seeing it a little more clearly. This is homework for what? Today's Wednesday. It's a third time. I think 4 is a charm. Lots of times, but there's problem number 2. Let's see, let's switch gears and then come back to this a little later. Let your brain move away from it and then come back to it. I think that has something to do with long-term memory and acquisition of skill. I don't have a degree in anything with neuroscience, but I do have 40 years of watching students learn math. So got to be something worth there. So let's look at y equals 4x cubed plus 3x squared minus 6x plus 1. And let's look at the absolute max from -2 to 2. Okay? And I'll be just listing your words of the day on the homeworks. And quick way to learn vocabulary is just to, look at a word and say, oh, I remember the definition for that. Look at the next one. 30 seconds, you probably go through 5 or 10 words. Do it every day. And unlike vocabulary tests where you learn 30 words and you get a test and you write the words down, and a week later you can't remember any of them, you actually can build some vocabulary this way. So let's do mnemonic right now. There's a nice mnemonic here. This kind of looks like a window, right? Those brackets, right? And when you're looking for absolute max and mins, you got to check the endpoints. You got to check on this window, -2, what value do we get at -2? At +2, what value do we get? So we're going to have to include -2 and +2, and we can get those numbers right now. So -2, -8, -32. I'll write it here. -32 plus 12, plus another 12 plus 1. I'm hoping that I didn't make any mistakes there. So 24 -8 plus 1, I'm getting -7. And if I made a calculation error, well, so be it. I just can't spend my life checking this stuff because I got too many videos and things to do. So I hope that's right. And +2. So we're back to, God, I hope I got this. 30, +32 plus 12, 44, 44 minus 12. Why did I? 44 minus 12, back to 32 plus 1, 33. All right, so those are the values of the endpoints. We're looking for the absolute max. Well, we can already count that out. All right, now the question is, all right, we know over here on this side of our window, we have a max of 33. I want to cut to the chase. 33. The question is, we had something that started here. Does it go above and then come back, or does it not? So we got to check to see if we have a max, which means we're going to look at the derivative, and on the left side, tangents are positive, and on the right side, tangents are negative. All right, so the question is, do we have a positive to negative? And if so, it's a candidate, and we got to go evaluate it. So we got to take derivative, which is 12x squared plus 6x minus 6. We might as well set that to 0. Might as well divide by 6. 2x squared plus x minus 1 equals 0. We want to factor that. Well, I guess I'll leave that there. So there's only one way to get these numbers, and that's a 1 and a 1. So the question is, we want a positive, so we want that one to be positive. We want that one to be negative. And so I've got candidates over here at 1 and -1/2. All right, one of those is going to disappear because we got sign changes, right? So we got at 1 at -1/2. I know that if I put a huge number in, that's going to be positive, right? And sign changes. Okay, so it's at -1/2. We go from positive to negative. We got to check this out. I wish it was the other one because I don't feel like doing the fraction work, but we're going to come back up here and do the fraction work. So -1/2 cubed is -1/8 times 4 is -1/2. -1/2 times -1/2 is 1/4 plus 3 is 3/4. And over here, -1/2 of -6 is +3, and that's a +1. Okay, so I can see 4. Okay, I'm not even close, 4-ish. I can stop right there because that's bigger. Okay, so I don't even have to finish it. So what was the absolute max? It occurred at the endpoint, 2, 33. Maybe I don't believe it. You know what? I kind of like to check to see if I made a mistake. So I think I'm going to graph this. I'm going to get practice graphing this real quick. Some quick. You try to graph it. See if you picked up anything this stage. I know I like to start with 1, going down at 6 to 1, coming back up, and then coming up fast. Oh, God, yes. Well, wait a minute. We said that within this window, there was a max and a local max and a local min. So what am I missing here? I thought I had a local max. Oh, the other side of the graph. Oh, yeah. Oh, my God. Yeah. We never did check this one out, did we? No, we didn't, because, or this one, I mean, the min, we never checked that out. We didn't care about it. So it looks like, we're over here, but that was our answer. So this was, yeah, it's starting to make sense now. 4-ish, this was 4-ish, but we're over here at 33. So I've looked at it from another perspective. I'm feeling good now. I wasn't there. Right now, I'm feeling good. I know that I should, something like that. I should play that song. I like that song. Yeah. All right, so, okay, so we got the little practice there. Here's one. You haven't seen this too much. You haven't seen this one too much, but let's see if you can knock it out of the park. Let's look at 8 and 1 plus 25x squared. All right, dx. Okay. Yeah, I haven't looked at that too much, but I'm hoping that you can spot arctan. Yeah. And u is what? U is 5x, right? Because if you did the arctan of 5x and I asked you to take a derivative of that, I hope you would say is, 5 over 1 plus 25x squared. That's what I hope you'd see. And I'm hoping that we're doing enough u substitution now that it would be nice if that's what we had. Because if that's what we had, that's what we got. And I got a marker in my hand. I'm going to give you that. I'm going to move this out. There it is. Yep, there it is. Oh, but I just made this 40 in the numerator. I just made it 40. I don't want 40. I want what? I want it to come back to 5. Oh, yeah. How do I get the number 5 out of 40? Oh, I forget what I wanted it to be 8. See, I confused myself. Remember, the original problem was 8 over. So I wanted 8. Geez, you know what? If I multiply by 5, I think if I divide by 5, I think the job's done. I think I just found that that's equal to 8/5 the arctan of 5x plus c, of course. Oh, okay. Well, that's what that was. So I hope some of you are starting to see that as a skill. Where now, I think I told you a month ago, a month from now, some of you might not have to write the letter U. Maybe you just can look at it and start doing them. I have a feeling some of you are there. Let's see if we can get everybody there by the end of the trimester. I'm doing a homework with you. I almost forgot. So 2 ways to find, and I want to do this problem because I know some folks haven't had much experience with the ln of x and really don't know what they're looking at in that graph or what its purpose is. And so I thought I'd try to shore up a little of those gaps from previous terms of study. So let's see if we can find the integral. Let's see if we can find the area bounded by y equals the ln function from 1, x equals 1, to x equals 4. And let's do it 2 ways. Let's do it first in terms of x, and then let's do it in terms of y. All right, and that'll give us a chance to talk about the ln function a little bit for those who have a non-working knowledge. The ln. It's pretty hard to talk about the area under a curve if you don't have any familiarity with the curve, all right? Or what the ln function is for. Might as well talk about it right now. The ln function has absolutely no purpose unless those numbers are on top of the letter e. These are the exponents you put on top of e, all right? And what are the exponents you put on top of e? Well, if you want to create an exponential function, then you're either working with negative y values. These are negative y values, and these are positive y values. For instance, that y value, 2, gets me in the ln function approximately 0.7. So 2, 0.7 gets me 0.7. All right, and this number has no meaning unless you put it on top of e. And e to the 0.7 is approximately 2. So the ln of 2 is 0.7, which means that if I want to create the function, the doubling function, which is 2 to the x, doubling things, it's pretty much the same as e to the 0.7x. Okay, so the ln function allows us to convert every exponential function out there, but in e notation. So if 3 gets me 1.1 approximately, then 3 to the x is approximately e to the 1.1x. Now, why historically was this so important? Well, think of the derivative of e to the x. It's itself. So you've got a calculation, a position, a velocity, and an acceleration function that are all the same. All right, and that's why the world turned towards e to the x in terms of computers and calculators and everything else to start studying how exponential functions change, because then the manipulation was pretty straightforward. All right, so that's a little look at that. And negative y values, right? E to the negative 0.7x is approximately 1/2 to the x. That exponential function. Because negatives do what? What do negatives do? What's pi to the negative 1? They reciprocate. Okay, so you got growth to the right of 1, decay. These are all the decay functions, because I could do that forever. I could go 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, right? And I could do that forever. That's why there's asymptotic behavior at x equals 0. All right, that was a crash course in ln of x. Unfortunately, crash courses don't stick with you too long, but that's why I don't teach sequential mathematics. In Algebra 2, we do ln of x day 1 of the course because it's one of the harder topics. And then we do it for the rest of the semester. All right, so first thing we do is graph. There's our ln function. Again, x equals 0. We know 1 gets us 0. And we know that 4, see now your rules of logarithms come into play. Not going to get into it. This is the area from 1 to 4. We'll just put the x's in from 1 to 4. All right, so we've practiced this, I think, extensively. Just the calculation. What measures that area? Each one of these things has a height of whatever the x is, the ln of x. And so the ln of x dx from 1 to 4. That's it. Now top minus bottom. The bottom is 0. ln of x, top minus bottom. We don't write the minus 0, of course. Okay, it's pretty straightforward. Now the question is, how do we do it in terms of y? I hope I got a marker here that's a little better. This one's starting to die. All right, so now we're not going to do vertical rectangles. We're going to do horizontal. It's not much better, but we'll get through it. Okay, do I have one in my pocket? Yes, I do. I'm trying to get repetition, my friend, as in come prepared. There we go, coming prepared. So if I look at this horizontal rectangle, the question is, is that a vertical width or horizontal width? It's vertical, which means we have to do it in terms of dy. And what's our mantra for dy? Right minus left. Well, I know what the right function is. Okay, that's that x value. That x value is 4. The question is, how do I get these x values? All right, well, I'm sorry, not these, but this dotted line x value. How do I get that? Well, I got to take away that x distance. From what? From 4. I got to get that from 4. And that's what's going to get me all of those horizontal distances. Okay, so I got to take this amount. Okay, and that's an x. Oh, well, ln of x equals y. Then what does x equal? E to the y. All right, so I have to name the x's in terms of y. So I now have a new function, and it is e to the y. All right, and so what is this particular distance? 4 minus e to the y. And so now know I'm integrating 4 minus e to the y dy. All right, that gets me these x distances. So for instance, the coordinate 4, well, I won't do 4, I'll do 3. I'll do 3. Okay, here's 3. 3 gets me 1.1. Okay, and I want at 3, that means that this is 1.1. That's 1.1. So what is this x distance? What is this x distance at 1.1? Well, we look at 1.1, we plug it in, we get that x distance, which is 3. So if this is 3, oh, I should have been here. Oh, I'm up here. So I'm up here at 1.1. That's a distance of 3, but I want this horizontal rectangle. I want that x value. I want that distance. Why don't I say distance? Well, that distance would be coming from 4 minus e to the 1.1. So hopefully you can see that this is about 1 unit long. It assigns that amount. All right, now the question is from what to what? Well, we have to know the ln of 4. I might as well show you. I know a lot of people never did any of this. So 4 is actually 2 times 2 is 4. 2 is e to the 0.7 times e to the 0.7 is equal to e to the 1.4. You add up the exponents. That's where your rules of exponents are coming from. That's the ln of 2 plus the ln of 2. All right, once you learn those numbers, then you more clearly see your rules of logarithms. And I think that a lot of people kind of never did any of this study, unfortunately. Okay, and we're trying to catch it up in the second part of the term because we have covered all the calculus concepts. So now we can try to fill in some of those gaps that people have. All right, so we're going to go from 0 to 1.4. That's an approximation. The exact answer would be the ln of 4. Okay, so we're going to continue to do those now. For those of you who didn't learn that last term, it's important. It's important. Otherwise, you have no feeling for e to the x or ln of x. So we got to keep talking about it. All right, I went off on a tangent right here. I did. I went off on a big tangent. That's right. It's calculus class. I guess I can. All right. All right, next problem. Let's see. Not too much more to do. Just, let's up our level here. Let's take the derivative of sine of x squared. Let's find y prime. Just some quick practice, y prime. All right, so pause the video, see if you can find it. I'm just going to play with it. Implicit differentiation. So we got x squared plus y squared times 2x plus 2y, y prime. There it is. That's what I'm after. Equals 5. So I'm going to divide by cosine. 5 over cosine x is actually the secant of x. So I am going to do secant over on this side. I'm going to do 5 secant of x squared plus y squared. Right? Because really what I had was 5 cosine x squared plus y squared. This is multiplication here, right? Multiplication becomes division. All right? So now this has gone to the other side. I've got plus 2x. That's going to be minus 2x. That's gone. I'm going to divide by 2y. And there it is. Stated implicitly, y prime. Okay. Then I'm just going to show you one quick thing. And we're done. Yeah, that's it. That's the practice. I just want to show you a logarithmic differentiation. I'm not going to hold you accountable for this, but I do think you should see it because it might be something that you hit at a college level. So, how do you handle something like that? Well, logarithms. ln of y equals ln of x to the x. Rules of logarithms. This is x to the ln of x, right? And this is ln of y still. Okay, now what do we do next? We could do e to the here, I believe, but typically we continue with logarithmic differentiation, which is 1 over y prime. That's what we're after, is equal to the derivative on this side, which is product rule. So that's 1 times ln of x, which is ln of x plus x times 1 over x. We'll clean that up a little bit. Y prime is equal to y times ln of x plus 1. And we know what y is. It's x to the x. So y prime is x to the x times ln of x plus 1. I just wanted to show you that, right? Because I'm not going to hold you accountable for it, but it does branch into another way of handling some polynomials that are tricky using logarithms. So just at least a brief introduction. That's that. All right, and you can practice the basic 8 if you want. If you feel secure in that, you don't need to. But if you got a lot of blanks on that last midterm, you probably want to do them. All right, and